Can entropy increase even when there is no heat exchange? At first, it might seem like the answer is no. After all, in many textbooks, entropy is closely linked with heat transfer. But in reality, entropy is a broader concept. It is not just about energy or temperature. It is about disorder, uncertainty, and the number of possible arrangements that a system can take. But what exactly is entropy? Entropy is a measure of how many microscopic ways the particles in a system can be arranged, even if the system looks the same from the outside. The more options the particles have, the higher the entropy. It's like comparing a neatly arranged bookshelf, low entropy, to a bookshelf where the books are randomly scattered, high entropy. But how can entropy increase without energy being added? Let's take a simple thought experiment. Imagine a box that is divided into two halves by a wall. On one side, there is a gas. On the other side, it's empty. Vacuum. The gas molecules are all moving around, bouncing off each other, but they're stuck on one side. Now, suppose we remove the wall. The gas molecules immediately spread out to fill the entire box. Did we heat the gas? No. Did we add energy? No. But entropy increased. Why? Because now the gas molecules have more space to move, more possible positions to occupy. The number of microscopic arrangements, what physicists call microstates, has increased dramatically. This is entropy increasing due to a change in configuration, not due to energy exchange. Here's another everyday example, shuffling a deck of cards. Imagine you start with a brand new deck, perfectly ordered from ace to king in each suit. That is a very low entropy state. It's highly organized. Now shuffle the deck thoroughly. What happened? You didn't add energy, but the number of possible arrangements has skyrocketed. The deck now has extremely high entropy. Again, no heat was involved, but entropy went up. So can information systems show this kind of entropy increase? Yes. Consider a computer memory chip. If you erase data from it, the system goes from a known, ordered state to a more random one. The entropy of the memory device increases, even though we are not necessarily adding heat to it at that moment. In fact, the famous physicist Rolf Landauer showed that erasing information has a minimum entropy cost. This connects thermodynamics with information theory. Another question, can living systems decrease entropy? Locally, yes. Your body builds cells and tissues in an organized way, which decreases entropy inside you, but this comes at the cost of increasing entropy in your surroundings by consuming food, producing waste, and releasing heat. So globally, total entropy still increases. The second law of thermodynamics remains untouched. One more visual example. Think of a puzzle. All the pieces are packed neatly in a box. Now shake the box. The pieces are still there. Their total energy hasn't changed. But now they are scrambled. More disordered. The entropy of the system has increased, and you didn't need to heat it up to make that happen. Entropy is about the number of ways things can be arranged, not just how much energy they have. Systems can become more disordered, more entropic, just by removing constraints, mixing or shuffling. No heat is needed. That's why entropy can increase even when there is no energy exchange. Entropy quantifies the number of microscopic configurations consistent with a system's macroscopic state, independent of heat flow. In statistical mechanics, increasing entropy corresponds to the system exploring more accessible microstates, even if no energy crosses its boundary. For an isolated system, spontaneous processes like mixing or diffusion drive the population of states toward maximal disorder. These reorganizations within the system's own degrees of freedom raise entropy without requiring heat exchange. Thus, entropy increase is fundamentally about information and probability, not necessarily energy transfer. When a gas spontaneously expands into an evacuated chamber, its entropy rises despite no heat entering or leaving the container. It's like shuffling a deck of cards more thoroughly, increasing the number of possible card orders without adding or removing any cards. In free expansion, a gas in a vacuum-sealed container is allowed to occupy a larger volume without performing work or exchanging heat. The macroscopic internal energy remains constant, yet the entropy increases because the molecules now have more positional microstates. This irreversible process illustrates that entropy can rise purely by enlarging the accessible phase space. No energy crosses the container walls, so temperature and internal energy stay the same. The drive toward maximum randomness underlies the entropy gain. Opening a valve between two chambers, one filled with gas and one vacuum, lets the gas fill both, increasing entropy without heat. It's like pouring marbles into a bigger box. Their total energy doesn't change, but the ways they can arrange themselves multiply. When two different ideal gases mix in an insulated vessel, no heat or work is exchanged with the environment. The final state has higher entropy because molecules are more uniformly distributed, and distinguishability increases the count of microstates. The process is spontaneous and irreversible, driven solely by concentration gradients. Thermodynamically, the entropy of mixing depends only on the change in composition, not on energy transfer. This demonstrates entropy rise via information loss about which molecule was where originally. Removing a partition between helium and neon gases at the same temperature and pressure causes mixing and an entropy increase without heat flow. It's like merging two colored sands in a jar. Once mixed, you can't tell which grain came from which pile, increasing disorder. Certain chemical reactions proceed spontaneously in an adiabatic, insulated system, increasing entropy even though no heat crosses the boundary. For instance, decomposition reactions can increase the number of gas molecules, thus expanding the system's microstate count. The reaction's internal energy distribution shifts among products, conserving total energy but creating greater molecular randomness. Entropy production is tied to irreversibility in new molecular configurations, not to external heat. Such reactions highlight that chemical disorder alone suffices for entropy growth. Calcium carbonate decomposing to calcium oxide and carbon dioxide in an insulated bomb calorimeter increases entropy without heat transfer. It's like shattering a single Lego structure into many pieces. You haven't added energy from outside, but the possible ways to reassemble pieces skyrockets. Molecules in liquids or atoms in solids diffuse to equalize concentration, even when the container is perfectly thermally insulated. Each particle's random walk increases the number of accessible positional states, raising entropy. No net heat flows. The process is driven by entropic forces and concentration gradients. Over time, diffusion smooths inhomogeneities, maximizing disorder. This underscores that entropy increase can occur through spatial rearrangements alone. Dye molecules spreading uniformly through a gel block in a sealed beaker raise entropy without any temperature change. It's like crowd members wandering randomly in a stadium until everyone is evenly dispersed. No energy is added, but order is lost. In information theory, entropy measures uncertainty or missing information about a system's state. Increasing entropy corresponds to losing knowledge of precise microstate arrangement, even if energy remains constant. Processes like randomizing bits in a memory register raise information entropy without energy exchange. This analogy connects physical entropy to data processing and shows that entropy is fundamentally informational. Thus, computations or erasures can increase entropy in a closed system purely through logical operations. Randomly shuffling a digital image's pixels increases Shannon entropy of the data without consuming additional computer power. It's like scrambling the order of pages in a book. You haven't added new pages, but the story's order becomes more unpredictable. Maxwell's demon thought experiment challenges the link between entropy and heat by sorting fast and slow molecules without work input. Modern resolutions show that the demon's information processing and memory reset incur entropy costs, preserving the second law. The sorting process itself raises entropy when considering the demon zone system. Even if the gas container sees no heat flow, this highlights that entropy accounting must include informational and measurement subsystems. It reaffirms that entropy can increase without direct heat transfer once all degrees of freedom are considered. A feedback control system in a microfluidic channel can separate molecules by speed, but its memory reset dissipates heat elsewhere. It's like a librarian reshelving books by title order without touching the books, but the librarian's note-taking and erasing generate more disorder in their notepad. Systems driven into non-equilibrium steady states by external forces can exhibit continuous entropy production internally without net heat flow to the surroundings. For example, steady shear flow in a Newtonian fluid inside an adiabatic container rearranges molecules, increasing entropy through viscous dissipation. Although total internal energy remains constant, microscopic frictional processes generate disorder. The entropy generation rate equals the work done by shear forces balanced by internal energy redistribution. Thus, maintaining a non-equilibrium state can raise entropy absent of heat exchange. A rotor stirring a viscous fluid in an insulated cylinder increases entropy through internal viscous heating, even if no net heat leaves the cylinder. It's like kneading dough in a sealed bag. The dough warms internally and becomes more mixed, raising disorder without leaking heat. In quantum systems, decoherence transforms pure states into mixed states by entangling them with unobserved degrees of freedom, increasing von Neumann entropy without energy transfer. This loss of phase information arises from unitary evolution of the overall system conserving energy. The system's reduced density matrix acquires statistical mixtures, reflecting irreversible information loss. Entropy increase here is about losing coherence, not about heat flow, and underpins quantum to classical transitions. Recognizing decoherence as entropy production expands the concept beyond thermal contexts. A qubit coupled to a spin bath loses coherence over time, raising its entropy while its average energy stays fixed. It's like a choir gradually going out of sync. No one sings louder or softer, but the harmony disintegrates into noise.